Hello, my esteemed viewers. It's always a great pleasure to have you with me on this channel. And in this video, I'm going to continue our discussion on Introduction to Quantum Mechanics. In the previous video, we looked at the brief description of quantum mechanics, and there's some of the contrast between quantum mechanics and classical mechanics. And in this video, we are going to take that conversation further. Now, part of the difference between quantum mechanics and classical mechanics rests upon measurements of quantities in both theories. In classical mechanics, measurements are quite certain or deterministic. Measurements are said to be deterministic in quantum mechanics because every measurement made can be given to a precise degree of accuracy. However, in quantum mechanics, measurements are quite non-deterministic, and this is because of the nature of quantum mechanics itself. The formulation of quantum mechanics requires probabilistic interpretation. This means that quantum mechanics can be interpreted as relying on the theory of probability to interpret some of the variables. The indeterministic nature of quantum mechanics is expressed by the Heisenberg uncertainty principle. The Heisenberg uncertainty principle stated clearly that it is not possible to make a precise measurement of the position and velocity or momentum of a quantum particle simultaneously. Now, for instance, it's not possible to give an accurate location or the precise location of an electron and its velocity or momentum at the same time. So these are some of the interpretational difficulties that arise from quantum mechanics. Now, on the other hand, in quantum mechanics, a quantum particle behaves both like a wave and a particle at the same time. And this is what we call the wave-particle duality. Unlike what we have in classical mechanics. In classical mechanics, a particle is either a particle and a wave is treated as a wave. But in quantum mechanics, a quantum particle exhibits both a particle-like property and then also a wave-like property. So these are some of the differences between quantum mechanics and classical mechanics. Furthermore, in the mathematical formulation of quantum mechanics, one of the easiest, the simplest mathematical formulation is the Schrödinger equation. The Schrödinger equation gives a simple mathematical formulation of quantum mechanics, and this equation can be stated in its simplest form as I, then the first derivative with respect to time of the wave function is equal to the Hamiltonian operator of the wave function. Now, the left hand side, I represent the imaginary unit of complex numbers. This is the first derivative with respect to time. Now, this quantity here is called the wave function, which depends on position coordinate and the time coordinate. Then on the right hand side, this H represents what we call the Hamiltonian operator. The Hamiltonian operator operates on the wave function. Now, the Hamiltonian operator gives the total energy of the particle in question, and this gives us the sum of the potential energy and the kinetic energy. Now, other formulations of quantum mechanics include the path integral formulation of Richard Feynman, we have the phase-space formulation, and then we have the quantum field theory in curved space-time, and so on and so forth. Now, there are several interpretations of quantum mechanics. Notable among them is the Copenhagen interpretation. We have the many-world interpretation of Everett. Now, the Copenhagen interpretation is attributed to Niels Bohr and Werner Heisenberg. We have other interpretations such as the quantum logic. We have the von Neumann interpretation. We also have the relational quantum mechanics. We have the hidden variable interpretation, and so forth and so forth. Now, some of these interpretations are quite contradictory to each other. Thank you.